Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on August 4th, 2025, about 5 days ago. The Big Hook, a compact 3 billion parameter traffic controller that generalizes zero-shot to new road networks and unusual incidents, explains its decisions, and in real deployment, shortened average queues by over 5% while roughly halving operator workload. The paper is titled Traffic-R1, Reinforced LLMs Bring Human-like Reasoning to Traffic Signal Control Systems, and as we'll see later, the implications for city-scale deployment are quite significant. It blends human-informed offline reinforcement learning with open-world online training and asynchronous multi-intersection coordination. Building on that, the tweet highlights an LLM-controlled traffic system already deployed in a major Chinese city, reducing congestion and on-site workload for over 55,000 drivers daily, moderate engagement. Alright, this schematic walks through the whole loop. Inputs on the left, the learning and reasoning in the middle, and the final signal decision on the right. Building on that, the bottom checklist compares controllers across 6 needs: zero-shot generalization, incident handling, efficiency, performance, explainability, and multi-intersection coordination, showing the reinforced language model as the only one ticking all boxes. Next, the figure lays out the two-stage training. On the left, offline human-informed reinforcement learning takes text observations, rolls out several answers, extracts only the actions, scores them with a rule-based reward plus expert validation, then updates the policy with group advantage and KL regularization. On the right, open-world online reinforcement learning loops through simulator steps, accumulates multi-step rewards, and performs TSIM-PO updates for the actor. Next, the diagram contrasts 2 coordination styles. On the left, every intersection observes and acts at the same time. Then the environment updates, which can cause conflicting choices. On the right, intersections take turns in 2 inner steps, passing short messages so neighbors react in the next inner step, enabling orderly, human-like cooperation across the network. Now, this table sets the stage for experiments. It lists the 2 real-world datasets and their traffic intensity. GNN uses a 3x4 grid, 3 recordings, with around 6,000 to 5,000 vehicles, and mean arrivals from roughly 360 to 524 per 5 minutes. Hangzhou uses a 4x4 grid, 2 recordings, with about 3,000 and nearly 7,000 vehicles, and a wider arrival spread, peaking above 1,100. Moving to the results table, it compares average travel time and average waiting time across 5 networks, with smaller being better. Traditional and reinforcement learning controllers trail by a wide margin. Even very large language models slip on some grids. The compact 3 billion model consistently posts the best or second best numbers, especially on Hangzhou 2 waiting time, while staying zero-shot across all splits. Building on the results, the big takeaways are clear. A compact 3 billion parameter controller can generalize zero-shot across cities and incidents, while staying explainable and fast enough for edge chips. The 2-stage reinforcement learning pipeline, plus asynchronous coordination, is the practical unlock for real deployment. That is it for this episode of AI Research Roundup. I am Alex. Thanks for listening.